Okay, we're going to be starting section 6.2 here today. This is discussing if you have random variables, what happens if you were to transform a random variable by adding, subtracting, multiplying a value to the random variable, and then also what happens when you're combining two random variables. If you recall from chapter 2, when we were first introduced to linear transformations on data sets, that's when we were discussing what if you were to add or subtract a constant value, we'll call that A, to every single observation in the entire data set. We looked at how that affected measures of center and location, measures of spread, and measures of shape. We said that when you add or subtract, that will definitely impact all of your measures of center and any measures of location by simply adding that constant or subtracting that constant to those measures of center and location. However, measures of spread, measures of shape would remain unchanged by that transformation. If you were to multiply or divide every single piece of data in your data set by, say, a constant b, then in addition to that impacting measures of center and location by multiplying those by b, it also affected the measures of spread by multiplying those by b. The one exception, however, was the variance. The variance was affected by multiplying by b squared. Okay. When we move to looking at how random variables are impacted through transformations, you're going to notice here that this is exactly the same rules as we learned in chapter 2 regarding transforming data sets. So and we'll look at what we mean by transforming a random variable here. But in essence, the bottom line is whether we're dealing with data or whether we are dealing with random variables, the effects of a linear transformation are exactly the same in terms of adding and subtracting are only measures of center and multiplying and dividing are only measures of spread and center. Shape remains unchanged. Okay, so we're going to start with an example that we actually had talked about in the last section, and that was looking at El Dorado College. They were looking at students and students who are taking between 12 and 18 credits. We were letting X be our random variable, which was the number of credits that a randomly selected student would be taking at El Dorado Community College. And you can see the probability associated with the number of credits taken here. Okay, in the last section, we had learned how to find the expected value, okay, which is the mean of your random variable. There's a formula on the formula sheet. We said you need to be showing those first few calculations, but then ultimately you can use one variable stat to get the mean, particularly helpful when you're trying to find the standard deviation. Okay, you would input these in L1, L2, and then you would grab this value from your screen to state what the standard deviation would be for the random variable X, number of credits. Okay, and we can see here that the expected number of credits, we would interpret that as alluding to the fact that we're talking about if you were to do this repeatedly. So if we were talking about many, many students and they were randomly selected, the overall average number of credit hours that is taken is roughly 14.65. Again, recall that we are not rounding that. Okay, our interpretation for a standard deviation of 2.06 would be for a randomly selected student, the number of credit hours typically varies from the mean, which is 14.65, by about 2.06 credits. Okay, all of that is what we had discussed in the last section. But now what we're going to look at is we're going to take a look at what if we were to perform a transformation on the random variable. For example, let's suppose that El Dorado Community College, they charge $100 for every credit hour, and then they have a set fee of $500 to cover technology costs for each student. Okay, so we're now going to let a new random variable, C, be the total cost of tuition in dollars that a randomly selected student pays. Okay, and so in symbols, we're going to express C as, now again, recall up above here, X represents the number of credit hours that a student is taking. So if we're trying to calculate what the total cost would be, and it's $100 for each credit hour plus a set fee of $500, we would say we're going to take 100 times X. Typically you use a capital letter when you are referring to random variables, okay? So X is the number of credit hours, 100 times X plus 500. Okay, this is going to calculate what the total cost of the tuition in dollars would be. Okay, so now the question is, what would be the expected cost of tuition for a student, and what would be the standard deviation of the tuition for the students? And so you can see we've kind of performed here a transformation on the random variable X, and so we can use this as a formula to calculate what the new measure of center would be, the mean, and the new spread would be for this data set, okay? And so how this will work, our new expected value is essentially going to be, now please recall here that we just got done reviewing that any measures of center are totally impacted by both multiplication as well as addition. So I should take the mean of the random variable X, that's going to get multiplied by 100 and then have 500 added to it. Okay, so if I look up above here, we had said 14.65 was in fact the measure of center, the mean for the random variable X. And so I'm just basically substituting that in, and that tells me that the expected tuition cost is roughly $1,965. If we were to select many students at random, the average cost of tuition would be roughly $1,965. Okay. Now for the measure of spread, if I were to do something similar here, okay, but please keep in mind we're talking about measure of spread, and so now when I look at what has been transformed, we know measures of spread are actually only impacted by multiplication, not by addition or subtraction. So I'm only going to apply the transformation to that involves multiplication here. Okay, so again, I look back up and I say, okay, we said that the standard deviation for X was 2.06. So I'm going to multiply 2.06 times 100, and I get the standard deviation of the tuition costs to be 206. Okay, in terms of the shape, I'm just going to make a remark here because it did say to describe the mean, the standard deviation, and how the shape would have changed. I'm going to say that the shape stays the same. Okay, the shape should stay exactly the same. Okay, that's what we mean by transforming a random variable. Okay, so let's look at another problem here from start to finish. Okay, on this problem, it says, in a large introductory statistics class, the distribution of X, okay, this is our random variable, X is the raw score of a test, was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. Okay, again, they were alluding to the fact that the shape was approximately normally distributed. So I'm going to put that capital N. I'm going to put a small x there, just denoting that this is the center and the shape and the spread for the random variable X, the raw scores. It says, though, the professor decides to scale the scores. That means he's going to curve the scores. And how he's going to do that is he's going to multiply all of the raw scores by 4, and then he's going to add 10. Okay, so the question here is, define the variable y to be the scaled score of a randomly selected student from this class, and then find the mean, standard deviation, and shape of y. Okay, so here would be our description for how we would be getting y through the transformation here. It said we are going to multiply x by 4 and then add 10. Okay, so there's our definition for the variable of y. Okay, then it asked us to kind of go through and discuss what the center is for y. Okay, so this would be mu sub y. Okay, measures of center are impacted by both multiplication and addition. Okay, so I'm going to essentially take my measure of center for x, which is 17.2. That will get multiplied by 4. I'm going to add 10. So the measure of center for the scaled scores or the curved scores is now 78.8. Okay, then I'm going to move on here and talk about the spread. Okay, the standard deviation for y. Okay, this would only be impacted by multiplication. Okay, so I'm only going to be multiplying the initial measure of spread, which is 3.8 times 4. That's going to give me the new standard deviation to be 15.2. Okay, and then in terms of shape, remember that's going to stay the same. We can see that the shape for the random variable x was approximately normal. Okay, mentioned that up here, approximately normal. So I'm going to call this also approximately normal. Okay, and then I'm just going to kind of put all those pieces of information together, and now I'm going to put a small y there, denoting that all of this information is describing the center, the shape, and the spread of the random variable y, which are the curved or scaled scores. Okay. Now, when I move down to example B is asking, well, what is the probability if we were to randomly select a student that their scaled score would be at least a 90? Okay. Now, keep in mind, we're talking about the scaled scores. These are the y values. At least means greater than or equal to. Okay. So I'm actually needing this information right here, okay, the scaled scores. Now, I'm allowed to use the normal CDF feature or the table A because I know that the shape of the distribution for y is approximately normal, okay? So that allows me to use normal CDF, okay? Remember, there are 4 inputs here. Just to kind of help guide us through this, I'm going to draw a very small normal curve, okay? We know that the center of these scaled scores is 78.8. We're looking for what is the probability that any score would land 90 or greater. Okay, so we need a lower bound, which would be the 90. Our upper bound is going all the way back into the tail, so we're going to call that 10,000. And then we need the mean and the standard deviation. Please keep in mind, again, these are the scaled scores, so this is from the random variable y. Okay, that typed into the calculator will roughly give us 0.2306. We're looking at roughly a 23.06 chance that a randomly selected student would have a curved score of at least a 90%. Okay, you're going to see how this is all kind of starting to pull together here, things that we've learned about normality in Chapter 2, and then in Part C to this, things that we've learned about probability in Chapter 5. It says here, assuming that the score of each student is independent of every other student, okay, meaning if you know something about one student's score, it doesn't influence or impact the probability of another student's score. It says here, if you were to select 4 students randomly, we want to find what is the probability, oh, here's that phrase, that at least one of the scores is above a 4. Above a 90. Okay. Keep in mind, we're talking, though, not about selecting one student. We're talking about having selected 4 students. Okay, so when we see that at least one, we know that, okay, this is asking us what is the probability that at least one, and it's a really good idea for you to write down at least 1 in 4 of the scores are above a 90. Okay, at least 1 in 4 is above a 90. Okay, so we know that when we see at least 1, that means 1 minus the probability that none. Okay, so we're going to say none of the 4 scores are above a 90. Okay, all right, so I need to figure out just what is the probability that a student, just one student scores less than 90. Okay, one student scores less than 90. Okay, Bailey, I apologize. Riley, sorry.
Yes?
I'm still making a video. Desi needs to go outside.
Okay.
My apologies. Okay, so the probability that a student scores less than 90. Okay, less than 90. Okay. That is 1 minus the probability we got in part B. Okay, remember, this probability was that they scored 90 or above. Okay, I'm looking for what if one student scores less than 90. Okay, one student scoring less than 90 is 0.7694. Okay, now why would I want to know what one student's odds of scoring less than 90 is? Well, I want to subtract over here that none of the 4 students scored above a 90. Okay, so what I'm wanting to fill in over here is going to be 1 minus, I'm going to fill in the odds of one student not getting above a 90. Okay, that's what this means. One student not getting above a 90. But remember, there are 4 students. So we're talking about 4. I need to make my exponent here a 4. Okay, so we're saying 1 minus the probability that none of all 4 of them score above a 90. Okay, well then I'm putting in here the probability that they score less than a 90, and I need to do that to the 4th power to account that I'm talking about 4 students that would happen for, and that would come out to 0.6496, which is roughly 64.96%. Okay, those problems are tough when they give you the at least one. Okay, you gotta kind of figure out, what the odds of not one student getting that, and then if we're talking about a group of students, that becomes your exponent. Okay, the last thing in this video that we're going to discuss then is what happens when you're combining together 2 random variables. Okay, we talked about what happens if you just have one random variable and you perform a transformation on it, addition, subtraction, multiplication, division. But if we wanted to combine 2 random variables together, okay, so let's say that we wanted to combine together x and y. We were going to add them, and by adding them together, okay, we create a new random variable that we'll just call t. Okay, then by adding the 2 random variables together that result in the random variable t, what would be the expected value for t, or what would be the mean of the random variable t? Okay, well, if we're going to add together x and y, remember through addition, we can do this with measures of center. All you're going to do to get the mean of the random variable t is you're going to add the mean of x and the mean of y together. Okay, so generally here, the mean of the sum of several random variables is simply the sum of their means. We're going to be able to look at an example of this to kind of spell this out. But here's what's really, really important with this. Technically, before we should or can combine random variables together, we have to make a determination that those 2 random variables are absolutely independent of one another. Okay? If they're not independent of each other, when you start combining together their means or trying to do things with particularly their measures of spread, that's when we can get in trouble because things start overlapping. Okay, the 2 random variables have to be completely separate. And just a recollection here from the previous chapter, what does it mean to be independent? It means if knowing whether any event involving the random variable x alone has occurred, okay, it technically tells us absolutely nothing about the occurrence of any event involving random variable y alone, okay, or vice versa. Okay, if that is true, then we can say that x and y are independent random variables. Okay, so knowing something about one can tell us nothing about the other. Okay, let's just look at examining some ideas of that just to make sure we kind of get the hang of that. Down below here, we see that the random phenomenon is to select a random male from the U.S. population, and we're selecting a random female from the U.S. population. We're going to let capital M be that male's height, and capital W will be the random variable for the woman's height. The question is, do we think that these two random variables, M and W, these two heights, would be independent events? Okay, so if I told you the height of the male that we randomly selected was 6'2", do you think in any way that would tell you anything about what the woman's height would be that we randomly selected? Okay, and that wouldn't tell us anything. I don't think that would give us any information about what the women's height would be if we knew what the male's height would be. Okay, because these are two completely separate selections that we're making from the U.S. population. And so because they don't tell us anything about each other, that means that yes, they are independent. Okay, so we're going to say a randomly selected male, or I should say male's height, tells us nothing about a randomly selected female's height. Okay, that means that they're independent. Therefore, if we were wanting in a problem to try to combine these random variables together, we could completely do that. It would be fine, and whatever the average heights would be, they could be combined together there. Okay, let's look at this next one though. Here, the random phenomenon is to select a random two-gender married couple from the U.S. population. So now we're selecting a married couple at random. Okay, we're going to let X be the husband's height, and Y is essentially the wife's height. Now we're asked the same question here. Do we think that X and Y are independent events of one another? Now, think about this. If I were to tell you that we randomly selected a couple and the wife was 6 foot tall, do you think that knowing that would in any way possibly tell you something about what her husband's height could be? Okay. Now, it's not always true, but you do notice that in a lot of couples, generally the husband tends to be taller than his wife. Okay, not always, but that is usually the case. And so if you knew that a wife was 6 foot tall, it would probably give you some indication that the husband is likely taller than 6 foot. So for that reason, when we're answering whether these two random variables are independent, I'm going to respond no, because knowing a wife's height may tell us something about the husband's height. Okay? Okay, and so we take a look at combining the random variables, and the key here, and this is particularly true of combining random variables and trying to combine together their measures of spread. Okay, you always need to make sure that you're asking yourself whether the assumption of independence of your two random variables seems reasonable. Okay, and so when we talk about the variance and combining them together, the two random variables absolutely have to be independent. Okay, now this is going to be a little different maybe than what we're used to. You'll notice here, when we're talking about combining two random variables X and Y into a new random variable T, this box is mentioning combining variance. It's not mentioning combining standard deviation. Okay, so if you are going to add together two random variables, as we discussed on the earlier page, their mean is exactly what you would expect. It is simply adding together the means of those two random variables. Okay, however, you should never add together the standard deviations of the variables to get the standard deviation of the sum. Okay, instead, you should be adding the variances of your variables, again, only if those variables are independent. Okay, so you're going to kind of use the variance almost as a stepping stone to help you get what the standard deviation would be of the combined random variables. And I want you to just think of this as the Pythagorean theorem. Okay, what this represents is the standard deviation of the combined random variables. Okay, but you're not going to add the standard deviations of the two separate random variables together. Instead, what you're going to do is you're going to square the standard deviation of random variable x, which makes it the variance. You're going to square the standard deviation of random variable y, which makes that the variance. You're going to add those two variances together, and once you have added them, you then take the square root of that sum to then reveal the standard deviation of the combined random variables. And that is actually what we do when we are doing the Pythagorean theorem. Okay, we don't get the hypotenuse from adding the two legs together. We get the hypotenuse by adding the square of each of the legs. Oops.